Hello everyone. Here we are going to discuss about the module 2 topic fiber alignment and fiber connector, fiber couplers, fiber splices and the different type techniques under fiber splices or a different type of connectors we are going to see. So the first point where we are going to discuss about fiber alignment and joint loss. Fiber alignment, we can define this fiber alignment condition with the help of the Fresnel reflection condition. So a major consideration with all type of fiber to fiber connection is optical loss at the interface. The Fresnel reflection, we can define it as when the two jointed fiber ends are smooth and perpendicular to the fiber axis and the two fiber axes are perfectly aligned. A small proportion of the light may be reflected back into the transmitting fiber, causing attenuation at that particular point. Uh, the Fresnel reflection we are defining like when two jointed fiber ends are smooth and perpendicular to the fiber axis, the two fiber axes and need to be perfectly aligned so that the one fiber axis and another fiber axis, whenever we are connecting, their fiber axis should be aligned each other. The small proportion of light, if it is reflected back, that reflected light which I just need to be calculated what the attenuation condition which is going to be occurred. So like everything light is cannot pass whenever the joint I just done between the two fibers, light cannot be transmitted fully, so some amount is reflected back, that I just cause in terms of attenuation at that particular joint. So this what we call it as Fresnel reflection with respect to the optical light. So steps say changes in refractive index at the jointed interface, that is what we are going to be identified. So normally we have the Fresnel reflection, we have standard formula, that is the classical Fresnel formula we are defined as in terms of for light of normal incidence as R equal to n1 minus n divided by n1 plus n whole square, where the R is the fraction of the light reflected at the single interface, n is nothing but the refractive index of the medium between the two jointed fibers, or n1 is the particular refractive index of the code region which is considered. So we are going to be calculated R, that is the fraction of light which is reflected at the interface. So whatever the amount of light is interface reflected back, that we are calculated in terms of R. So we using with the help of n1 and n are refractive index factors. So this R, if I suppose I calculate, then I can able to find the reflection fiber light reflection, fiber reflection whatever I considered earlier. So with respect to that loss, we can calculate in terms of decibel using this particular equation. So loss in terms of decibel due to Fresnel reflection at single interface, we can calculate loss is equal to minus 10 of minus 10 log of 1 minus r with base 10, which is considered. So this will be determined the optical attenuation due to the Fresnel reflection at the fiber to fiber joint. So between the fiber to fiber joint, we are going to identify the optical attenuation loss we are going to be calculate with this equation. The effect of the Fresnel reflection at the fiber to fiber connection can be reduced through the use of index matching of fluid, so in the gap between the jointed fibers. So suppose the Fresnel reflection can be reduced, so the reflection factor, if it is more, the loss will be more. So this will be controlled with the help of something fluid, if it is index matching fluid, if it is introduced between the gap of the joint of fiber. So this loss can be reduced with that particular condition, we can reduce the loss. So one problem we are going to be discuss with respect to the this particular problem, like an optical fiber has a core refractive index 1.5. Two length of the fiber are connected together. Two length of the fibers are connected together. Assuming the fiber axes are perfectly aligned, and calculate the optical loss in decibels at the joint with the help of here as specifically mentioned, this problem is with respect to Fresnel reflection when there is a small air gap between the fiber end faces. So we are going to identify the solution in terms of Fresnel reflection condition. So whatever the given information, I just need to be noted down. N1 is 1.5. Two length of fiber is connected, assuming that fiber axes are perfectly aligned. Calculate the optical loss. So when there is a small air gap in between the fiber end faces, so N, I can say air gap, that is N is equal to 1. So N is equal to 1, N1 is equal to 1.5. So I can need to calculate R. Then I just have to calculate the loss equation. By using that, I have to find condition. So this solution for that particular problem is mentioned in this slide. So whatever I just said, n1 is 1.5, n is equal to 1. So after simplifying, I'll get r is equal to 0.04. So using a Fresnel formula, loss is equal to loss optical the after because of the reflection loss, I just have to calculate with this equation. So loss of Fresnel, which is equal to minus 10 log base 10 1 minus r is calculated here. So 0.4, 1 minus 0.04 is 0.96. Log 10, I have to use it for 0.96. So into 10 minus 10. So loss, I just get it in terms of 0.18 dB. So but the question is asked for the two end faces, what will be the total loss? So that is what we are saying. The consideration symmetry is a clear optical loss at the second phase also 0.18. So 0.18 and 0.18. So total 0.36 dB is the total loss of Fresnel reflection at the fiber joint is going to be considered. So this is how the final answer will be. Loss will be 0.36 dB. This is the amount of loss which is going to be happened with respect to the fiber connection. So coming to the point which I just I can add it with respect to the reflection with respect to the Fresnel. There are inherent connection problems when jointing fibers with the for instance. So the fiber joints with respect to the instance, we can list it out different core and cladding diameters. This is also the connection problem. This will also give the connection problem. If suppose I say the core is a different size, or core the length is different compared to the another fiber. Whenever the fibers are connected, one end of the another end, if it is connected, if I have the core is not matching, if suppose cladding is not matching with respect to its diameter, so it is cannot be perfectly aligned. So core is trying to connect to the cladding also, or cladding is connect to core also. This is the inherent condition, inherent connection problem which will give with respect to when we are jointing two fiber ends. So there is another particular condition is, suppose I have numerical aperture is different, relative or even delta is also different, either numerical aperture or delta is different, that is also gives a different problem. Loss will be more with all these conditions. If suppose I have different refractive index profile, if suppose I used graded index fiber, then refractive index profile will come into picture, alpha values come into picture. So if alpha is different, then of course there will be a loss will be more whenever we connecting two fiber ends. Fiber faults also the problems whenever the connecting of fiber ends. Core ellipticity or core concentricity is also an issues with respect to the fiber fault. So these all different kind of variety A, B, C, D, whatever I mentioned here. So this will always going to be give the connection problem with respect to the whenever the fiber ends are joined. So the loss will be more because of all these reasons. The loss caused by the above factors are called intrinsic joint loss. That is one kind of joint loss. So this is the point with respect to the joint loss. However, I just mentioned the fiber alignment is earlier. So based on the alignment, we just discussed the Fresnel reflection factors and loss also, alignment loss, the total loss with respect to jointing loss. So this is also the point how the intrinsic joint loss is going to be obtained. So with all these four varieties are going to be defined the intrinsic joint loss. So another different variety of the jointing loss will be in terms of the misalignment loss. So the misalignment means one fiber ends are not aligning with another fiber. So fiber ends are not aligning properly will give an misalignment. We'll also call it as mechanical misalignment. These conditions, coupled compatible optical fibers. This misalignment usually can be done in three dimensions. One is longitudinal dimension misalignment. You can see it in that diagram A, this is a longitudinal misalignment. There is a large gap between two fiber ends. Maybe it is aligned, perfectly aligned with respect to the fiber axis, but there is much gap, air gap is going to be there. So passing information from first end to the second end, it is very difficult, because in between we have air gap and it can reflect and it can go out. So this will be a longitudinal misalignment. And the second diagram is the lateral, radial or axial misalignment. But these are the different names which is considered. This type I can also call it as lateral misalignment, or something like radial misalignment, or even axial misalignment with respect to the axis. So axis is not matching of one fiber end to the another fiber end. So this will give a loss, again missing some information from core to the core is not passing, moving away out of the region of the another fiber. So the last of mechanical misalignment is in terms of angular misalignment. So the one fiber axis not aligning, it is aligning with respect to the another fiber axis with respect to some angle theta. So there are angle difference between the fiber axes from first to the second. So with this is in terms of theta, which is what we consider. So this will be an angular misalignment. So the optical losses resulting from these three types I just mentioned earlier, lateral, longitudinal, and even the angular misalignment, all these misalignment we can dependent on the fiber type, or what is the core type, core diameter, and what is the distribution of the optical fiber between the corresponding propagating modes. These are all the factors are going to be important while defining the three mechanical misalignment whatever I considered. So there is two graph here, you can see the first and second. So first graph I'll just discuss about the first graph, the loss with respect to the misalignment which is defined here. So the loss in terms of insertion loss characteristics are jointed optical fiber due to the lateral and longitudinal misalignment with respect to the graded index of fiber with the 50 micrometer core diameter, if I suppose considered. So what could be the loss factor? So insertion loss will be more with respect to lateral misalignment comparing to the longitudinal misalignment. Longitudinal misalignment, if suppose I say the longitudinal misalignment, fiber axes are aligned, but there is a much large gap between the two fiber ends. So maybe the light can be travel in the with respect to axis maybe same, and the loss might not be much comparing to the lateral misalignment. If I say lateral misalignment, there is a few portion of one fiber end is not connected to the another end, that is clearly open. So if I take two pipes are connected, if it is not connected, half it is connected, half is open, means water is going to be lost much comparing to the longitudinal misalignment, if I want to say it. So hence lateral misalignment will give more insertion loss comparing whenever one fiber end to the another fiber end, the information need to be inserted. So coming to the second graph, this will give the insertion loss for jointed optical fiber due to angular misalignment. So this is again insertion loss with respect to the angular misalignment. If angular misalignment with respect to the here considered step index fiber. So suppose the numerical aperture with respect to the air gap with 0.22 and air gap is 0.22 here numerical aperture, but it is I just used a different variety of index matched gap. The loss will be more, which is going to be considered with respect to the angular misalignment, as the degree of displacement is more. You can consider as the angle of degree is a more degree in terms of more misalignment considered. The of course the value of loss will also be more. Here also the same, as the distance displacement is more, the loss will be more. The two graphs will give the reality how the loss will be going to be produced, and with respect to the mechanical misalignments. Here mechanical misalignment is very important topic, and prior the problem what I just discussed with respect to the Fresnel reflection, or the loss with respect to the fiber alignment loss, that is also very important. So the same loss which I taken with respect to the multi-mode fiber joints. So whenever two fiber ends are connected together, so that is if I take it with respect to the multi-mode fibers. So the lateral misalignment reduces the overlap region between the two fiber cores. The overlap region or area between both fiber cores approximately gives the lateral coupling efficiency. So the lateral misalignment with respect to the multimode fibers, this will give always the in terms of lateral coupling efficiency. So neta lateral will can be calculated in terms of 16 of n1 by n whole square divided by 1 plus n1 by n whole to the power 4 into 1 by pi, and it is multiplied again with the 2 cos inverse of y by 2a minus y by a, which is multiplied 1 minus y by 2a whole square whole to the power half, where y is going to be a lateral offset of the fiber core axis and a is the fiber core radius with respect to the optical fiber. So whenever I just calculated neta lateral, then I can calculate the loss of with respect to that misalignment loss in terms of minus 10 log of neta lateral divided by base 10 in terms of decibels. Some loss which we will calculate in terms of lateral misalignment with the help of this equation. Next, the lateral misalignment loss in terms of multimode gradient index fiber. Previous what we discussed the multimode gradient index fiber with the lateral misalignment. Now lateral misalignment with respect to the multimode gradient index fiber. So lateral misalignment loss was dependent on misalignment was dependent on the refractive index gradient alpha for small lateral offset. Then we can calculate LT is equal to 2 divided by pi, which is multiplied by y by a, and which is multiplied by alpha plus 2 divided by alpha plus 1, where the y is lateral replacement or the offset which we considered earlier. So this is having a value lies between 0 to 0.2a, where a is considered in terms of the core radius, which is earlier also mentioned with respect to the equation. So lateral misalignment with respect to the multimode gradient index fiber, we will use this equation to be calculate. So this here neta lateral is required to be identified. However, with respect to the previous mentioned about lateral misalignment, neta lateral is required for lateral coupling efficiency. Then I can calculate 1 minus LT will give 1 minus of this LT will give neta lateral, so that I can use next loss is equal to minus 10 log of neta lateral will give the total loss in terms of decibel for lateral misalignment with multimode gradient index fiber. Suppose if I used the parabolic refractive index profile with respect to multimode gradient index profile, then alpha is equal to 2. So if alpha is equal to 2, you can substitute here. So LT you will have some value that is 8 by 3 pi into y by a. After simplifying all this, substituting alpha equal to 2, you will get this equation as a 0.85 into y by a, that is equal to LT. So you have to substitute this value. 1 minus a 0.85 into y by a will give neta lateral, that is the lateral coupling efficiency. Then you can calculate total loss with respect to the parabolic profile multimode gradient index fiber. So with respect to that, we'll discuss one problem. So a step index fiber has a core refractive index is 1.5. So we have step index fiber. Keep remember this. I have core refractive index is n1 is equal to 1.5. Core diameter d is equal to 50 micrometer. So I just require a as per the previous equations. So a is nothing but radius. Radius is 25 micrometer. The fiber is jointed with the lateral misalignment. So we can understand here lateral misalignment between the two core axes of 5 micrometer. So core axis, the lateral misalignment is about with respect to 5 micro. So why I can mention in terms of 5 micrometer. So estimate the insertion loss. I just have to calculate insertion loss at the joint due to the lateral misalignment, assuming a uniform distribution of power between the all guided modes. When there is a small air gap between the joint is considered with the index match. So I just have to calculate two times insertion loss. One is with respect to the air gap n equal to 1, and another one is joint index matching, that is n is equal to n1. So that is the condition. So 2 times I just have to calculate insertion. See, let us see how to solve this. The problem is with respect to the multimode step index, I just have to be considered, because given question is in terms of step index fiber. So lateral efficiency I can calculate using this equation. Neta lateral is equal to approximately equal to 16 of n1 by n whole square divided by 1 plus n1 by n whole to the power 4 into 1 by 2 pi, well, sorry, 1 by pi into 2 times of cos inverse of y by 2a minus y by a. It is multiplied by 1 minus y by 2a whole square and whole to the power half, which need to be considered. Oh sorry, 1 minus y by 2a whole square, that whole to the power half I just need to be considered. So here just substituting the value. So I said y is equal to 5 micro and a is 25 micro as the given information, and n1 is 1.5. If suppose I used index or air is considered, then n is equal to 1. So with that substitution I will get neta lateral is equal to 0.84. So for this neta lateral, insertion loss due to the lateral misalignment minus 10 log base 10 of neta lateral. By substituting that, I will get the loss neta lateral with respect to the small air gap, which is 0.95 dB. Suppose thus the lateral offset, if I suppose considered index matching profile, if I suppose used. So what is going to be happen? N1 is equal to N. So this one is cancelled each other, this one is also cancelled each other, so cancels. Okay, means it's 1 2 2 to the power 4, 2 to the power 4 is 16 plus 16, it is cancelled each other, so this term is becomes 1. So into 1 by pi, so 2 cos inverse of y by 2a into, and the rest of them is same. So where y is equal to 5 micro and a is equal to 25 micro, so micro cancels. However, so after simplifying, this neta lateral is 0.82872. The insertion loss with respect to that I'll get 0.59 dB. So the loss will be reduced comparing to the index matching profile suppose used comparing to the air gap earlier. So the loss is going to be reduced with respect to the step index fiber under lateral misalignment. Here we considered lateral misalignment case. There is a second variety of problem with respect to the similar condition, but here we used multimode graded index fiber. So graded index fiber has a parabolic condition, alpha is equal to 2. So I just directly I can take LT is equal to in terms of 0.85 y by a I can consider. So the core diameter which is mentioned here, that is 50 micrometer, a is equal to 25 micrometer. Then estimate the insertion loss due to the 3 micrometer lateral misalignment. So y is equal to 3 micrometer at fiber joint when the index matching, assuming there is uniform illumination of all guided modes and there is a uniform illumination of all guided and leaky modes. So there is leaky modes with respect to the uniform modes. So the solution for this, so there are two cases. Let us take the first case, the leaky mode we will consider later. So the earlier case is a uniform illumination for the guided modes with respect to misalignment. Use lateral misalignment in terms of a guided mode where alpha parabolic profile is considered. So alpha is equal to 2. With respect to that, we earlier with respect to the equation directly I just simplified LT is equal to 0.85 y by a. So y is 3 micrometer, a is equal to 25 micrometer, micro cancels. After simplifying LT I can get, so coupling efficiency I can calculate neta t is equal to, neta lateral is equal to 1 minus LT I can use it. So to get a 0.898 and loss lateral insertion loss minus 10 log base 10 of neta lateral in terms of I'll get 0.47 dB. So if suppose I used uniform illumination for the both guide and leaky modes, then the formula with respect to that is going to be changed as 0.75 y by a. Instead of 0.85 we will have 0.75. So simplification will get it in terms of the same condition however we did earlier with respect to the a condition. So we'll get a 0.41 dB as the total loss comparing to this. So leaky mode, if I suppose I consider, then the loss can be reduced with respect to the graded index fiber. So the same condition, now I just need to be consider lateral misalignment. Now I am considering angular misalignment loss. So angular misalignment loss at the joints of the multimode step index fiber, I considered step index fiber with respect to that angular misalignment with the angular coupling efficiency neta angular, which is equal to 16 into 1 n1 by n whole square divided by 1 plus n1 by n whole to the power 4 into 1 minus theta n theta divided by pi n1 into 2 delta to the power half, where theta is equal to angular displacement in terms of radians. Consider delta is the relative refractive index difference of the fiber. The total loss now I can consider minus 10 log base 10 of n angular neta angular. So that is total angular misalignment loss with respect to the step index fiber. So we'll see this with respect to the problem for this. So directly answer, I just consider you can solve this in terms of the taking of the earlier equation. So multimode step index fibers have numerical aperture 0.2, 0.4. Numerical aperture is 2 step index fiber. Numerical aperture 1 is 0.2. Numerical aperture 2 is equal to 0.4. So respectively. So both have core refractive index as a core refractive index n1 is equal to 1.48. Estimate the insolation loss at the joint in each fiber cost 5 degree angular misalignment. Theta is equal to the loss is 5 degree. So the solution for this, I just taken angular misalignment with respect to the 5 degree. I cannot take it. It should need to be converted degree into the radians. Pi into pi by 180 need to be multiplied. So that is what theta need to be considered. So assume that medium of fibers used in between that here. So n is equal to 1. So with respect to that, using the equation neta angular can be calculated with respect to the equation. So we'll get the answer for neta angular first case with numerical aperture is 0.2, total loss is 0.98. If suppose numerical aperture if I increased, so I found the loss is going to be reduced. So this is how just I can identify the solution. You can try it at home. So I can move further with respect to the fiber to fiber intrinsic loss. The factors which is matching, what is the factor going to be important whenever the fiber to fiber intrinsic loss? So it comprising a mismatch in the fiber core diameters, a mismatch in the fiber numerical aperture, and differing fiber refractive index profile, that is also be considered. So some intrinsic coupling losses at the fiber joints. One is see, you can see the core diameter is different of one fiber end to the another fiber end. So this will give something loss, intrinsic loss or coupling loss, which we can also say it because of diameter are mismatching. So over here numerical aperture from one fiber end to the another fiber end is different, it is not matching, so mismatching again. Alpha parabolic profile one is another one is different fiber profile, so that is also not matching. So all these particular have something factor onto the intrinsic loss between the fiber to fiber connector. So all modes are equally excited in the multi-mode or graded modes, and the numerical aperture and index profiles are the same, then the loss resulting in the mismatch is in terms of core diameter. Then I can calculate all are matching but core diameter is different. So the loss is in terms of core diameter is in terms of minus 10 log base 10 of a2 by a1 whole square in terms of decibel, where a1 a2 are the core radii of the transmitting and receiving fiber respectively. So loss all terms are matching, like numerical aperture, index profile, everything is matching under step or gradient index fiber. So but only the mismatch with respect to core diameter, then the loss we can calculate with respect to minus 10 log base 2, sorry, base 10 of a2 by a1 whole square. So that is, we can use it. Suppose a2 is less than a1, so that condition is important, else it is 0. So the loss is mismatching with respect to the numerical aperture. Everything is matching except numerical aperture. Then the loss is calculated in terms of numerical aperture minus 10 log base 10 of n2 by n1, na2 divided by na1 numerical aperture. That is term na means so whole square in terms of dBA. So numerical aperture 2 is should be less than numerical aperture 1. That is was the point. So suppose mismatch with respect to the refractive index profile, then everything is matching, but no refractive index profile is matching. So minus 10 log base 10 of alpha 2 into alpha 1 plus 2 divided by alpha 1 into alpha 2 plus 2 decibels, where alpha 2 should be less than alpha 1. In that case, else it is 0. So intrinsic loss obtained at a multimode fiber to fiber joint with respect to all together, all are mismatching. Alpha mismatching, numerical aperture is mismatching, and the a is mismatching, that is diameter term is also mismatching. So then loss is due to intrinsic loss with respect to all factors is minus 10 log base 10 of a2 into na2 whole square divided by a1 into na1 whole square, also alpha 2 into alpha 1 plus 2 divided by alpha 2 plus 2 into alpha 1. It need to be required where all the cases a2 greater than a1 and numerical aperture 2 greater than numerical aperture 1, alpha 2 greater than alpha 1, else it is 0. So this is what all the possibility equation with respect to intrinsic loss with respect to the factors. That is the factor what I considered here, numerical refractive index profile, and also numerical aperture, and also diameter or radius of the fiber to fiber connector between either graded or step index fiber. Suppose if I take the single mode fiber joints, only single mode, if suppose I consider rather than multi-mode, then we can also use to calculate the loss lateral misalignment or angular misalignment, or even the diameter with respect to the misalignment, all the three different misalignment we can calculate it. So start with the first one, that is angular misalignment. The total loss I will calculate in terms of t1 due to the lateral offset with respect to the y which is considered. So t1 is equal to 2.17 y by omega whole square dB, where omega is the normalized spot size with respect to the fundamental mode. So omega can be calculated with respect to the spot size. For LP01 we can calculate it with respect to the empirical formula. Omega is equal to A into 0.65 plus 1.62 V to the power minus 3 by 2 plus 2.88 into V to the power minus 6 whole term divided by root 2. Where omega is the spot size, in terms of micrometer we will get. A is the fiber core radius, is the normalized frequency for the fiber. So once you calculate normalized spot size, then you can able to calculate the total loss with respect to angular misalignment for the with the lateral offset of y with the single mode fiber. So the insertion loss TA caused by an angular misalignment, that is in terms of theta which is considered at a joint in a single mode fiber, then total loss TA is equal to 2.17 theta omega n1 into V divided by A n1 NA whole square decibel. So that loss is angular misalignment with respect to the insertion loss with the theta. So with respect to this, we are going to see on problem. So single mode fiber having following parameter: normalized frequency V, we have core refractive index is mentioned, and core diameter to A is equal to 8 micrometer. Numerical aperture is 0.1. Estimate the total insertion loss of a fiber joint with a lateral misalignment of 1 micrometer and an angular misalignment of 1 degree. So lateral misalignment is also we have, and angular misalignment also we have. So I just have to calculate because of these two insertion loss. So one is T1 I have to calculate because of this 1 micrometer, and I have to calculate TA with respect to this. So we have a solution for this, but total loss in terms of T1 and TA need to be considered. So first I have to calculate normalized spot size. Both require omega. So omega can have formula from the empirical equation, A into 0.65 earlier we mentioned, and it's mentioned here. So V, which is given information, that is 2.4, I just need to be substitute, and I have to solve this. Substitute and simplifying, we get omega. So total loss with respect to the lateral offset y is equal to 1 micrometer. Just need to be substitute that term and get T1 as a 0.22 decibel. So loss due to angular misalignment theta, something like which is given 1 degree, but it should be in terms of radian. That's why 1 into pi by 180. So pi by 180. Omega is 3.12, n1 is 1.46, A is for micrometer, which is given 8 micrometer. Numerical aperture is 0.1 and V is equal to 2.4. So substituting and simplifying, we'll get 0.49 decibel. So this is the total loss because of angular misalignment. This is the total loss because of angular lateral offset. So together total loss is will be t is equal to t1 plus ta. So total loss is in terms of 0.71 decibel. So that's how we can find the solution with respect to the single mode fibers. What could be the effect of lateral misalignment and also angular misalignment? Using equation we can find the total possible loss with respect to the fiber connection. So next is a single mode fiber joints is with respect to a single mode of fiber with the joint. So calculation of the intrinsic factor which quite commonly occurs in the interconnection of the single mode fibers. So no losses are present due to the extrinsic factor. The intrinsic coupling loss will be in terms of a omega 1 omega 2 which is considered here, that is a spot size at this transmitting end and receiving fiber ends are different. So the spot size is different with respect to one fiber and another fiber, then we'll have a loss is because of intrinsic coupling loss, that is minus 10 log base 10 of 4 into omega 2 divided by omega 1 plus omega 1 divided by omega 2 whole to the power minus 2. So this is will give the in terms of decibel. So equation therefore enables the additional coupling loss resulting from a mode field diameter mismatch between the two single mode fiber to be calculated. So this is how we just need to calculate the total loss. So we'll find the solution with respect to the same particular equation. Spot size are two different spot sizes. Two single mode fibers with mode field diameter which is considered 9.2 micrometers and 8.4 micrometer are to be connected together. Yeah, assuming no extrinsic loss, determine the loss due to the connection due to the mode field diameter mismatch. So the loss intrinsic is I can consider the spot size with respect to this factor as omega 0 1 and 0 2. I can take it and I can find the total loss in terms of 0.35 decibels. So next topic is fiber splice. So we'll discuss about fiber splice, a permanent joint formed between the two individual optical fiber. The permanent joint which is formed between the two optical fiber are known as a fiber splice. So the permanent joint between the two fiber ends will give the fiber splice. They establish a long hole for a long distance communication of optical fiber. There existence of one fiber end to join permanently joined with another fiber end. So fiber splice, that's why it is going to be more important. Splices may be divided into two broad category depending upon the splicing technique. So two methods are there. One is fusion splicing or called as so two types are fusion splicing and mechanical splicing, which is used to optimize the splice performance. So under fiber splicing, we are going to see the fusion splicing, or also called as welding, and another one is the mechanical splicing. So before doing any fusion technique, we have to prepare the fiber ends first. So that preparing fiber ends with the help of scribe and break technique, or score and break also, which can be called. Scribing the edges, optical fiber end preparations can be done. The principle of the scribe and break are going to be the edge, which is of the fiber ends are rolled over the curvy edge, curved mandrel, which is considered. So the something knife edge also should be there onto the other side. Something crack if it is there, I just need to be identified to the help of knife edge, which is clearly matching or clearing the fiber ends where we are pulling the fiber to the both ends or giving some tension and pulling. So the for splicing is that we are going to make the fiber ends smooth and square end faces for any particular fiber. So it should be clean. This knife head should be clean so that it should be in a square end. So scoring of a fiber surface under tension with a cutting tool which is going to be used. So this is a preparation how before doing fiber splicing we are doing some preparations. So next is fusion splicing. There is a first technique of a fiber splicing is a fusion splicing, can also be called as welding, which is accomplished by applying something local heat or arc, that is what considered flame or arc, electric arc, which is used to interface between the two butted or fiber ends, pre-aligned fiber ends, which is called as by two butted ends, causing them to soft and fuse. That is how we done earlier. The whenever heat is given to fiber ends, it becomes smooth, and it is by pushing to the two ends, then it will be joined together so that fiber connection can be done. Flames heating sources. Normally, the flames can be obtained due to the heating source with the help of microplasma torches can be used. The microplasma torches having argon and hydrogen as the material. Another one is oxyhydric microburners also as the source of our flame heating. Oxyhydric microburners consisting of oxygen, hydrogen, or alcohol vapor. The most widely used heating sources is an electric arc. So the apparatus or connections are like this apparatus for the fusion splicing technique. This is very important if the question is asked on to the fiber splicing, especially fusion splicing. Then you have to draw this particular diagram along with the earlier explanation is required. So two fiber ends are placed onto the fiber alignment groove very hold tightly with the fixed block, where the two electrodes are placed in between of these two blocks, where this is giving an electric arc between the two fiber sorry electrodes, electric arc which is going to be produced. So what I just need to do, the fiber ends are need to be pushed through the help of groove towards to the close, so that electrodes also give the electric flames over this particular junction. And because of the large amount of heat which is coming through the help of electrodes, this fiber end becomes melted together, and when you push it, it will get connected so that hold it tightly together. So this is what fusion splicing apparatus and how this is mechanically it is melt or developed with all these connections. And so the process which is mentioned in this particular diagram, how the fusion splicing can be done, schematic illustrations, however, with the previous, first fiber ends are not clear, so I just have to clear this fiber end. Nothing but electrode will give initial setting how we need to place. One fiber end is placed on the one fiber groove, another fiber groove where I placed this is the top view where you can find two electrodes onto the other side. And arrangement smooth surface tension like electrode electric arc, whenever it is produced, it becomes melted together so that smooth ends or curvy surfaces are going to be done. So move from the either end of the fiber or one end of the fiber at least pressed together, nothing but it is going to be pushed together so that it is going to be get connected. So accomplished something like a splices connection is then going to be observed over here. This is the overall process how the fiber splicing technique can be done with the help of the electric arc fusion. Okay, so multimode fibers gives average spice loss under this particular condition is 0.09 decibel. That is one total possible loss. So under this particular case, we are also looking for something like self-aligning phenomena which takes place during this fusion splicing. Before fusion, whenever sometime you are pushing two fiber ends, it is not clearly it is not matching. So what is going to happen, because two ends are going to be melted, so there will be something shift like between the core is not matching or fiber axis is not matching with another fiber axis. So while pushing it is just the spaces which is just going to be shifted. So during fusion, what is going to happen when the temperature or the tension, this is just pulled to the other side, but there's something which you can find after fusion, something like some just glitches you can find it at the core region of a two fiber end where it is connected. So this glitches or whatever we find it with respect to the junction of two fiber ends, so this will probably give to the loss for with respect to the total communication of optical fibers. So fusion splicing of single mode fibers have insertion loss below 0.3 dB. However, the 0.09 dB is with respect to one particular case which is mentioned, but with respect to a single mode fiber, loss will be, of course, in terms of some losses, but zero point 0.9 dB within that which is going to be defined. For a single mode fiber, one example which is considered how it is possible, single mode fiber fusion splicing over 31 kilometer link, the mean splice insertion losses are 0.18 and 0.12 dB at wavelength of 1.3 to 1.55 micrometer respectively. The mean splice loss will be 0.06 decibel obtained with fully automatic single mode fiber fusion splicing machine. So this is one of the reality which is however the loss which is going to be obtained. One example which is considered how loss is possible with respect to the fusion splicing method over single mode fiber over the distance of 30 kilometers. So by increases how the loss can be identified with respect to the fusion splicing machine, which we can list it out. So how it is going to be done fusion splicing? This is what the apparatus which is can be used. The reality Fujikara companies which is developed optical fusion splicing splices. This is a tabletop model and this is handheld device where one side of optical fiber is inserted, another side fiber end is inserted over here. This is electrical arc is going to become, so this is butted together over here at the junction. We can see it in the display unit where we can find even the same condition we can obtain over here also, two ends which is combined together over here. So the commercial fusion splices are produced various size of a handheld or to the laptop or in terms of tabletop, whatever the different size of variety of fusion splices can be developed. So splicing loss will be a zero point zero 0.01 or zero point zero 0.02 dB for multi-mode to single mode fiber respectively. So usual loss with respect to the priority. So something like drawback with respect to talking about fusion splicing will be the heat to fuse the fibers may weaken the fiber getting weaken, or sometimes if you pull it may break. The fiber fracture can be generally going to be happen at the heated affected zone. It may cut whenever fusing fluid joint. Next type is mechanical splicing. This is another type of fiber splicing. So here the fibers are held in alignment by some mechanical means. So with the help of mechanical, we are just aligning the fiber ends. So achieved by various methods, including the use of tubes around the fiber ends and weave groove into the which the butted fibers are placed together. So tube splices is one end, and another one is groove splices, also be called as V groove techniques. We'll see that in terms of diagram, the use of accurately produced rigid alignment tube into which the prepared fiber ends are permanently bonded. So one fiber end and another fiber end have to be bonded together in the mechanical manner. So the method to be used tube splice or the V groove technique what we are going to be used. So we can see that in terms of over here. First method is a snug tube splice as in terms of diagram A. Second method is a loose tube splicing. This is one type of the tube splicing method. Under mechanical misalignment, we are finding about tube splicing. In a snug tube splice utilizes a glass or ceramic capillary with an inner diameter just large enough to accept the optical fiber. So another method or another condition, we can have transparent adhesive is injected in the capillary to give the mechanical sealing and index matching of the splice. So two fiber ends are placed inside the another pipe. So one pipe which is used to connect the two pipes or to connect the two pipes. So we just have the how PVC pipe how we are going to be bonded. In the same manner we are bonding here in terms of glass or ceramic capillary tube. But in between this region where we are just using the index matching fluids can be used while doing this particular mechanical splicing. So this is one ceramic, and if suppose I have cross turned of fiber, then I can use the square cross section capillary can also be used, so that it is something like loose tube loose tube splicing. This is snug tube splicing. So two methods under tube splicing. This is one type of a mechanical splicing method. So the average loss, insertion loss with respect to this particular tube splice, especially for snug tube splice, is zero point 0.5 decibel loss will be more. The loose tube splice uses oversized square section metal tube. Even with respect to that is also be more in terms of multimode grade index fiber if I suppose considered. So the other common mechanical splicing technique is V-groove. So V-groove is very good method comparing to the tube splicing method under mechanical splicing method. The prepared fibers alignments of ends can be done through the insertion in the groove. The splice is made permanently by securing the fiber in the V groove with epoxy resin. So we can observe it in terms of V groove splicing technique under this particular diagram. So V groove splicing formed by sandwiching the butted end fiber ends between V groove glass substrate and a flat glass retainer plate. So we are placing two fiber ends in the groove, mechanical groove. So V groove substrate. This is pushed and forced together with epoxy resin placed in between. So this is how we can make it. The second diagram tells how it is going to be bonded after doing the pushing and together, and the plastic plate also going to be used and to be pushed together. So joint insertion loss because of this V groove technique, which is comparing to the snug tube splicing, which is much reduced as in terms of 0.1 decibel. So mechanical misalignment, mechanical splicing technique where V groove splices are very good comparing to tube splicing. The further variant on the V-groove techniques is another type under V-groove technique. We have elastic tube or elastomeric splice and comprise of two elastomeric internal parts. So elastomeric splices you can see in terms of diagram A. This is the cross section one side, and this is how the assembly is going to be done afterwards. The outer sleeve holds the two elastic part in compression to ensure alignment of the fiber in the V groove technique. So in the V groove, we are pushing two fiber ends and holding together in the elastic material. Slightly more complex groove splice, as known as a spring groove splice technique, a bracket containing two cylindrical pin which serve as a alignment guide for the two prepared fiber ends. So this is another type spring groove splice method. So these all come under mechanical splicing. First I saw tube splicing, next I saw V groove, next here we saw that is elastomeric splicing, and next we are going to see is about spring groove splice technique. So spring groove techniques, over here you can find something like a spring which is placed over the two fiber rolling fiber cylindrical pin, where optical fiber is placed here. This is two rolling cylindrical fiber. Over to that we are placing this particular spring. So we're pushing these optical fiber ends together to the other side. So expanded overview, here it is going to be give this need to be placed here. This is at the top, and next push from the either side of this fiber so that it is get connected. This is a cross sectional view, cross view of these together. The complete assembly was secured using the drop of epoxy resin have to be dropped in between these. The mean splice insertion loss because of this will be much reduced compared to the V groove technique. So 0.05 dB decibel. That is the amount of loss because of spring groove splice technique. So one more type under mechanical groove, that is multiple fiber splicing using a silicon chip array. So silicon chip array method, which is going to be used to multiple number of fibers are spliced together. Many number of fibers are spliced together. Multiple simultaneously fusion splicing of an array of fibers in a ribbon cable has been demonstrated for both multimode and single mode fibers. So here you can see the multiple number of fibers are there in the ribbon cable has been demonstrated for the multimode and single mode fiber, which is need to be connected. That's it. So this is all about fiber splicing. Next topic we are going to see about fiber connectors. So one fiber end need to be connected with another end. So this connection is possible with the help of the difficult to be achieved with respect to comparing to the more difficult this fiber connector methods comparing to the optical fiber, because fiber termination which protects the and locates the fiber end. The fiber end alignment to provide optimum optical coupling. The outer shell which maintain the optical connection and fiber alignment to protect the fiber end from the environment provides adequate strength at the joint. So insertion loss with respect to this fiber connection is going to be in the range of 0.2 to 3 decibel, much more large comparing to the earlier connection. So the essential requirement for good connector, so loss should be much small after doing the connecting one fiber to the another fiber. So connector should produce much less loss, and environment sensitivity, cost, reliability, or everything should be low and easy to assemble. Repeatability is required and interchangeability is also required. Fiber connectors may be separated into two broad categories. One is butt jointed connector and another one is expanded connector. So one type of fiber connectors we will see under rubber connector. So that is a ferrule connector, cylindrical ferrule connector, and its structure is shown in this particular diagram. The question is asked fiber connector. So the two types of fiber connectors you can explain. One is a ferrule and expanded beam is the next one. The structure of a Bach-Dual connector of a ferrule which is shown over the second diagram, but first diagram is going to be important. The structure of the basic ferrule connectors. Two fiber ends are connected with the help of some connectors, ferrule connector. So that is making the connections of two fiber ends can connected together with the help of something like an external sheath or external material. So that is what ferrule material which is used over here. So coming to the point with respect to these, the tool achieved the butt jointing with the optical fiber is called a cylindrical ferrule connector. That is the first type, butt joint. The two fiber so to be connected are permanently bonded with the help of something like epoxy resin in a metal plug known as ferrules, which have accurately drilled a central hole in their end faces. However, you saw in this particular earlier diagram. So metal plugs should be there. Something like just have to drill and I have to hole fixed that ferrules are together. So within the connector, two ferrules are placed in an alignment sleeve, which is using accurately machined component which is allows the fiber ends to be butt jointed. Some ferrule connectors have incorporated batch jewel in the ferrule end faces. That is one of the type of batch jewel can be used under ferrule. The use of the batch jewel allows the close diameter and tolerance requirement of the ferrule end faces. That is the advantage if suppose I use batch jewel. The jeweled ferrule gives the insertion loss in the range of 1 to 2 dB, so loss is much reduced comparing to the earlier case. Capillary ferrule is manufactured from ceramic material, usually this capillary ferrule is so aluminum, porcelain. So good application within the precision ferrule connector. So the material used, which are the type of ferrule, watch jewels, what is the use of that, and how these ferrule connectors are connected. So all together about a cylindrical ferrule connector, which is explained in this particular slide. So this is how the real-time image to mention about this particular capillary ferrules connection, ceramic capillary ferrule. So the multimode fiber connectors, how it is get connected. Typically, average loss of our multimode graded index fiber and single mode fiber within the precision ceramic ferrule is 0.2 to 0.3 decibel. So this is the real-time image how you can connect with it in terms of ceramic ferrule, capillary ferrule. So next is a duplex or multiplex the fiber connectors. So one or two many number of fiber ends are connected with the to the many number of fiber ends. So this is the strip of many fibers are there on to that you can see here ribbon fiber cable. Many fibers are there in this particular case. 10 fiber ribbon, which is 10 fibers are existed in this. They are connected together. So one end to the another end. So how it need to be connected? Something mechanical sleeve. V glue section, however, it is going to be there to be placed one end of that, and the other end is need to be connected. So multiple fiber connectors, fiber ribbon connector using V glue silicon chip, which is considered here. That is, this is for 10 fiber nodes. This is for multiple number of fibers are connected together with the help of connectors. So ferrule connectors again. So these are the fiber connector type, different variety of fiber type like SMA, FDDI, D4, ST segmented section of this particular SC, that is simplex or duplex also we can consider. We have different fiber connector type, ST segmented or SC simplex or duplex connections. You can see this is how real-time connection or shapes are mentioned with respect to fiber connectors. These are the real images of the all different type of fiber ends or connectors from one fiber end to the another fiber end can be connected. So you can see here these are the fiber one fiber end which is circulated or covered by the something like extra layers or protectors. So the normal system, this is how link can be happen from transceiver, transceiver fiber cable which is existed to be connected to the any particular transceivers, and it need to be connected. So next is fiber coupler. So type of fiber couplers, how can be coupled one fiber end to the another fiber end. So fiber coupler is a device that distribute light from a main fiber into one or more branch fibers. So generation of the noise and modal effect can cause a problem under this particular fiber coupler. So classification of fiber couplers can be done with respect to core interaction type or surface interaction type. So core to core interaction or surface to surface, fiber to fiber information are passing. So this is how the coupling can be done from one unit to the another unit of fiber ends. So normally the optical fiber coupler is a device distribute the light from main fiber into the another branch fibers or another fibers. So fiber couplers can possible different variety. It can have in terms of 3 or 4 port couplers, star couplers, wavelength division multiplexing devices can also be used. These are the different variety of fiber couplers. So application of this within optical fiber information distribution system, including data buses, LANs or computer network and telecom access network, we can define into many ranges or many types. These are the application area where fiber coupler can be used, but these are the different variety of 3 or 4 port star coupler or wavelength division multiplexing. So we'll see in detail with respect to all these together. So optical fiber couplers types which is mentioned here. The first diagram which says about three port coupler, three ends of a fiber and need to be connected here. Either multiplexing or demultiplexing can also be mentioned. Four star coupler or four port coupler, four ends are connected through the one branch, can be four port coupler. And the star coupler in terms of C diagram, many numbers, n numbers of fiber ends are connected together. So wavelength division multiplexing means here one wavelength is coming in another fiber, another wavelength coming, they are matching and passing. This is like a three port coupler, but wavelength are matched here. Wavelength multiplexing, wavelength demultiplexing. So that is demultiplexing or dividing into the so this is the different variety of fiber couplers which is mentioned here in a single diagram. So if I suppose want to see the in detail with the how 3 and 4 port couplers, the fabrication of this fiber can be done. So one is the lateral or offset method. So from this one end to the two which is segmented and going, so laterally which is done, and another method is semi-transparent mirror can be used. So under this particular type, of course, in a two cases losses might be going to be observed. So here the one light is divided into this and this, or one wavelength are shifted into this. So passing the information from one main channel into the another two channels. That is gives the three type of port coupler. Here the three port coupler can be obtained in the lateral offset method. So the other one diagram is semi-transparent mirror is used passing and reflecting the one information to the other side, and the other one is passing into the another channel. So three port couple in the three different manners. So light from one input is coupled to the output fiber according to the degree of the overlap or lateral offset method, and the other method is directional coupling capability with the help of multimoding, or something like a mirror which is used partially reflecting the surfaces can be applied directly to the fiber end faces with an angle of 45 degree to form thin film beam splitter. Semi-transparent mirror method that also can be adopted under 3 port or 4 port also possible. The complete range of these couplers have been developed which utilizes the beam expansion or collimation properties of a green rod lens, which with the spherical retro reflecting mirrors can be used. So the green rod lens are micro optic fiber couplers with respect to the parallel surface line. So this is the green rod method, or the particular green rod lens can be used to connect to fiber ends under 3 port and 4 port. So here also can be possible. So how it need to be, it can be directly passed or directly reflected from one unit to the another unit, and it can be passed. So this is normally going to be done with respect to the expanded versions with respect to the 3 port or 4 port with the help of green rod lens. So the first one, lateral shifting. Next is surface shifting, or the with the help of surface kind of shifting, which is can be done with the help of the manufacturing a coupler, like fused bioconical taper technique. So fused bioconical taper technique, which is the structure and principle you can observe it, is the operation for fused bioconical taper coupler. So one end of the fiber end, which is tapped together or fused together with the another end, so that if the one ray of light which is passing in one ray of light, which can be shifted into the something like whenever the fusing is going to be done, whenever I hit the light, which will be reflected or shifted into the next layer, and which can also be passed into the next optical fiber. So the information can also be reflected to the other end, refracted, reflected, everything is possible with this particular fused region, bioconical taper region. So this is also very important technique under fused coupling technique, fused bioconical taper technique, which can be employed. So the excess loss which can be defined with respect to all these coupling technique, the ratio of in terms of power input, power output, which can be mentioned. So 4 port coupler, if I consider, the excess loss can be calculated 10 log base 10 of P1 by P3 plus P4. That is how we can able to estimate from 1 to 1 2 3 4, if I suppose I taken. So with respect to the second port, the loss will be in terms of calculated in this manner. The insertion loss, however, is generally defined with respect to loss obtained due to port optical path. So insertion loss from 1 to 4, the information passing 1 to 4, the loss is in terms of P1 by P4. So that will give 10 log is 10. So crosstalk also we can able to understand it with respect to the measure the directional isolation of this ratio in under 4 port coupler. Crosstalk can also be mentioned P2 by P1. So 1 2 from one end, 3 4 to the another one, crosstalk from one to another. So P2 by P1 can be give the crosstalk. Finally, the splitting or coupling ratio indicates the percentage of the division of optical power between the output port, and again by using fused bioconical taper, the split ratio can be defined as P3 by P3 plus P4, which can be multiplied with the 100. That is what split ratio of information 1 and 2 to the 3 and 4. So with related to this, we are going to have one problem. So 4 port multimode fiber FBT coupler having information of 60 microwatt power, which is not in a port 1. The measured output powers at the port 2 3 4 is this much, like a 0.004 microwatt, 26 watt, 27.5 watt microwatt respectively. The I have to determine excess loss, insertion loss between the input and output port, the crosstalk, and the split ratio for the device which I need to calculate. So with respect to the given information, we have P1 is equal to 60 micro, and rest of the values we just need to be remembered. So excess loss with respect to the consider, we have to have a equation excess loss 1 2 3 4. So P1 to P3 and P4, we are going to take P3 plus P4. We know that we can from the given information P1 P3 plus P4 we can get it, and P1 we have. So simplifying, we will excess loss get as 0.5. Insertion loss from port 1 to port 3, port 1 to port 4, insertion loss can be calculated 10 log based P1 by P3, P1 by P4 can also be made it, and to identify insertion loss. Crosstalk between 2 and 1, so P2 by P1 with the 10 log base 10, so we can calculate the crosstalk and total loss. The split ratio, we can use the same equation P3 by P3 plus P4 into 100, so it will give split ratio also. This is how we can find the solution for that given problem under FBT. So the other type of couplers are star couplers. So you can find it many number of neighbor ends and connected, and in the random fashion which can be connected from one to any other. So this is going to be a mixing of that particular fiber ends were going to be connected. Or reflected back mirror can also be established here. The same light can be reflected and it hitted back into the another point and it is passing the information. So splitting loss usually under star coupler we can calculate 10 log base 10 of n is the number of fibers are going to be used to connect from the star coupler. So this is also the another form of a star coupler. You can observe it. The star coupler 8 to the 8, so 8 channel star coupler which can be obtained here. So the normally if it is in terms of n number, then I can use it to calculate excess loss under star coupler in terms of 10 log base 10 of p T divided by summation of 1 to n Pj, total power with respect to all the fibers which is received, which is inputted and which is received. So that ratio will give to excess loss with respect to the star coupler. So this is how we can find about we can have understanding about the fiber couplers also with all the different variety of couplers. So a very important concept under this particular 4 points, fiber alignment losses is also very important. You can expect a problem, or fiber connectors also going to be any very important. Fiber couplers, fiber splices also very important. So under fiber splice, one of the type we can expect under fiber splicing, any splicing technique can be expected, and fiber coupler you can expect any coupling method which is imported, or any problem however we mentioned in first technique of fiber loss we can expect some problem. So keep studying all these particular topics, very important. Thank you for listening about these topics.